This is problem 4 from chapter 15. In problem 4, each of the cables can sustain a maximum tension of 5,000 pounds. If the uniform beam has a weight of 5,000 pounds, determine the shortest time possible to lift the beam with a speed of 10 feet per second starting from rest. We are starting from rest and going to 10 feet per second, so during that time we're going to have an acceleration, which is pointing upwards. And they said find delta t min, so the acceleration is equal to the change in velocity over the change in time. They're telling us that the change in velocity is 10 feet per second. If you use delta t min for delta t in the denominator, that would give you the maximum acceleration. So you have A max is 10 feet per second divided by delta t min. The acceleration is going upwards. If you have acceleration going upwards, you have to have a net force pointing upwards. You have a component of the force of tension, which is pointing upwards. You have the force of gravity pointing downwards. So the greater the acceleration, the greater the tension in the rope. But we are told that the maximum tension is 5,000 pounds. So if we're using delta t min, that means we are at the maximum tension. You have a rope on this side and a rope on that side, so pointing upwards you have 2 times the y component of the tension. Remember that doing the impulse-momentum relationship is similar to doing Newton's second law. We have our impulse-momentum relationship here, equation 15.3. You can rewrite this by bringing mv1 over to the other side, and that would be m times delta v. And if your force is constant, as it is in this case, then you can pull that constant force outside. It's a net force because of the sum that you have here, so it's net force times the integral of dt, which is just delta t. So we can rewrite that as m times delta v is equal to F net times delta t. And because this came from Newton's second law, if you bring the delta t over to the other side, that would be m times a is equal to F net, which is Newton's second law. So we're going to use this equation to solve the problem. Just looking in the y direction, equation 15.3 is a vector equation. We are looking just at the y components here. And I have the mass times the change in velocity. The mass was given to me, well, the weight was given to me. So the mass is the weight of 5,000 divided by 32.2 times 10 feet per second is equal to F net times delta t. If I use delta t min here, that means the tension is going to be at its maximum value. And since I'm accelerating upwards, let's say up is the positive direction, this is 2 times ty minus mg. mg is 5,000. So I have to find what the y component of the maximum tension is. So you have a 5,000 pound force in this rope on this side, in the other rope on this side. If this is 5,000 and this is 3 feet and this is 4 feet, the y component is 5,000 times 4 over 5, which would be 4,000. And you have rope on this side and on this side, so that's 2 times 4,000, so this is 8,000 minus 5,000 times delta t min, which is what we are looking for. So now we can solve this. Delta t min is equal to what we have on the left-hand side here is 1,552.8 divided by 8,000 minus 5,000, which is 3,000, and that gives us 0.518 seconds, and that is the answer.